First law of thermodynamics. All right, like I said, what we just did for the last couple of days, just go over some basic terms, and we just did the lab on specific heat, so we know what that's all about. All right, but the first law of thermodynamics is the first step. Well, actually, that's not true. It's one of the first laws I ever taught you in Chem 1. What does the first law of thermodynamics? It is the first law. First thing I ever gave you in Chem 1 back like the first day of class. I did it. What's another way of saying the first law of thermodynamics? Which basically says this. There's another way of saying it. Okay, it's the total amount of energy in the universe is constant. What's another way of saying that? Conservation. Yeah, energy is conserved, and therefore energy can't be created or destroyed. Remember that? That was the first law I ever gave you. Matter and energy cannot be created or destroyed. Law of conservation of matter and energy. Basically, that's the first law of thermodynamics. We're going to get 3 laws. We're going to get about thermodynamics. All right. All leading up to, and I forgot to mention this the other day. I did in the air class, but I didn't hear you guys. When I first showed you how to do the delta H calculation, which you just did 8 of them in the lab, right? That delta H calculation can either be positive or negative. Negative means it was exothermic, right? I told you just briefly that favors spontaneity because everything seeks its lowest energy state, right? So negative delta H's would favor spontaneity. That's our first clue. Our goal, I forgot to mention this the other day, our goal in this chapter is to come up with, at the end, and we will, and be able to tell whether a reaction can occur or not. In other words, whether a reaction will happen. The first clue is delta H. The first clue is the enthalpy. All right, that's what I wanted to tell you. We're going to use enthalpy again here. All right, but the first law of thermodynamics says that energy can't be created or destroyed. All right, and this is, I told you I was going to show you how dumb I was back in the day. I remember distinctly doing this and getting the wrong answer over and over and over again in a class and not figuring out why. See what I did wrong here. My logic seemed to be sound. You know, energy can't be created or destroyed. Therefore, the heat loss has to equal heat gain, right? Yeah, write all that down. Heat loss equals heat gain. So I'll be doing the calculation. Delta H equals MC delta, MC delta T on one side has to equal MC delta T on the other side, and I'm getting the wrong answer every time. Why? Why is that calculation not technically accurate given the equation? And we've kind of run into this a couple of times in the problems.
You're saying negative something equals positive.
Exactly. Heat loss is negative. Heat gained is positive if I keep TF minus TI. The only way this is true is if I talking about the absolute value of the heats. So when I was doing that, I remember distinctly standing up there being embarrassed on my old chalkboard up there, and not wooden chalkboard. Yes, my old wooden slate. You know, like the Flintstones. I pedaled to work in my car like the Flintstones, and my feet were tired. And Dino, the dinosaur. No.
Yeah, so we all know.
All right, good.
Yeah, it was right where around.
Anyway, so a better way to write this, and a more accurate way to write this, is to say the heat loss plus the heat gained equals 0. And that's the equation we'll actually use, okay? Because if you use heat loss equals heat gained, you've got to do the absolute value of them. Otherwise, you'll get a negative on one side and a positive on the other. But if you do it this way, we can keep our equation, delta H equals MC delta T, where delta T is TF minus TI. We can keep it that way and not have to worry about it. So that's the end of the notes. Like I told you, this chapter is going to be very much like this. Yeah. No. As I've been trying to tell you, and you got to get used to this. This is much more like Chem 1 than Chem 2. I'm not going to be, like, a reason I could do this with only 25 minutes remaining in a class is that's the end of the notes. I'm going to do one example, and that's it. All right, that's what we generally are doing here. All right, let's do the one example. Copy this guy down. It's not like in organic, where I was pretty much going the whole period and doing a bunch of demonstrations and stuff like that. This is more Chem 1 stuff. Now look what I can do with this. It's pretty cool. I can predict, if I mix two things together, I can predict their final temperature. And that's what our next lab is going to be on. And I believe you're going to do this next lab tomorrow. Even though I have a lab scheduled for Chem 1 as well, I don't believe there's a lot of chemicals that have to be out for that lab, and I know there's not a lot for your lab. So we could probably do them on the same day, even though I don't like to do that.
Before the end of the year, are we gonna do a lab with like crazy, a lot of chemicals?
Yeah, I mean, I don't know
What do
about a
we
lot.
think Can we blow something up?
Yeah, let's put those same questions back up there. Can we eat it? Can we blow something up? Are we going to blow anything up today?
When do we do that little thing?
How many questions are on the test?
Thanks for the mail.
Does this count? How many points is this worth?
How many points will I get if I don't handed it on the day it's due?
I'm pretty sure you just.
How many points do you get if you don't hand it in at all, Allie?
Sweet, you said something else.
All right, so take a look at this guy. You're watching? Now, I need to do – this is an amazingly easy problem, and I'll bet you I'll be lucky. You'll be lucky if half of you get this correct. And even though I'll set it all up for you, and I'll stop after it's completely set up, and all I'll ask you to do is the algebra, because it requires you to be meticulous. It requires you to do them step by step by step. You can't just plug numbers into the calculator to get this because there's just too many variables. It's simple, basic algebra where the algebra never really gets any harder than. Really?
Oh.
Look at that. Did I do that? No. Like 2x equals 8. The algebra is never much harder than that. But because there's so many of it, so many of them, so many of the variables in different places, it actually is difficult and you have to do it step by step. Let's set it up. What would the equation be? I just told you the equation for First Law of Thermodynamics. What is it?
Heat loss plus heat gain.
Right. So delta H lost plus delta H gain equals 0. Heat loss plus heat gain equals 0. What?
Is that a little case?
Delta H loss plus delta H gain equals 0. So let's do this. Who's losing heat? Well, here, before I even do that, let's just do, I'm going to spread, and I want you to spread it out a little bit. MC delta T plus MC delta T equals 0. Spread it out a little bit more there. So we have the heat loss guy. That's how we're going to calculate him, using his mass, specific heat, and delta T. And the heat gained. And all we're going to do is have one variable that's going to be missing. Who's going to be missing in this one? What's it asking me for?
Final temperature.
Yeah, the final temperature, TF. Now, we actually kind of did this in one of the homework problems, I believe. But you did it in like step A, B, C. It broke it down for you. You didn't have to have it broken down. We can do it all at once in this kind of calculation right here. I remember that. I think that was the one that I did on the board where you had to. Only I think that one was actually solving for the specific heat at the end, wasn't it? This was solving for TF. Either way. All right. So let's do this guy. Who's losing heat, first of all? Which guy's going to be losing heat? The 100 degrees Celsius one, right? Because the other guy's you're going to mix hot water at 100 degrees with cold water at 10 degrees, okay? You're going to mix those two guys together. So what's the mass of the hot water? And make sure to write this small because it's all going to fit on one line. 120 grams. 120.0 grams. What's the specific heat of water? We'll make it easy for ourselves. We'll use 1 calorie per gram degree Celsius. Keep your units, especially in this problem. What's my delta T? It's TF minus TI, so it's going to be TF, which is the unknown, minus what's the initial temperature of the hot water? 100.0 degrees Celsius. All right, so there's my heat lost. Who's gaining heat? What's the mass of that guy? 250 grams times the specific heat of water is still 1 calorie per gram degree Celsius times what? TF minus TI. In this case, it's TF minus 10 degrees, 10.0 degrees Celsius. And the whole thing equals 0. I have just set that all up for you. There's nothing else to do but basic algebra. But I need you to do that. I'm going to give you 5 minutes to do, 5 or more minutes to do this. And I'll bet you half of you get it wrong.
Oh, I'm guaranteed I'll get it wrong.
And this is the problem. We have to get good at doing this. There's nothing that you don't understand about this. But you have to be able to do it meticulously, step by step by step. I'll probably do it in 3 more steps. And you should too. Okay? All you're doing is multiplying out, distributing, getting variables to one side or the other. It's stuff you know how to do. But you have to do it without making dumb mistakes. Try it.
You stop doing that.
Now, you may not know if you got the right answer, but one thing's for sure, guys. Where does the right answer have to fall?
Somewhere
Between 10 and 100. So if you get an answer like 125, you're wrong.
You know the right answer.
I don't. We're going to work it together. Let's see what we all got. My guess is the most prominent answer will be the right one. What'd you guys get?
Hold on, I didn't catch you.
Shut up.
Yeah.
I heard different answers.
39.2.
Yeah, 39.2.
Yeah,
Hold on.
but
Got L.
39.2?
yeah.
I don't see everybody having
I
39.2.
got 111.
There you go. You added hot water to cold water, and you got even hotter water.
I'm sure I did that too.
Negative 300%.
Rachel didn't get it either. Like I told you, be lucky if about half of you get it. So far, it sounds like about 4 or 5 of you got it.
What was the answer?
39.2.
What'd you get?
Yep. Like I said,
I got 111.
111. That makes sense.
Tom got negative 320.
That's even better.
370, my bad.
That's almost absolutely zero.
Oh wait, never mind. I know what I did. Maybe that's not right.
I know. I thought I was right.
That's because I was right.
Tomorrow's lab, by the way, we're going to do.
39 point what?
39.2.
I got it.
Whoa, Allie's good. All right, let's do this on the board.
33.
Now, look it. By the way, you know, one of the ways you can keep track of this stuff is by keeping track of the units. I've said that before. It's one of the ways I like to keep track of things and know if I'm doing it right or not. All right, let's see. I have 120 grams times 1 calorie per gram degree Celsius. What will happen there to my units? Grams will cancel, right? Right? And I'll get 120 calories per degree Celsius times TF. So that's 120 calories per degree Celsius TF.
It's the other way around.
Okay, now look up here. If you're not, whether you're done or not, you should be done by now. But look up here and watch. See what you did wrong. Okay. Now I have to do the same thing. I have to distribute this across to the negative 100 as well. So that's going to be negative 100 times 120, which is going to be what? 12,000, right? And that's going to be, now this time it's calories, right? And my units are degrees Celsius are still there, right? So it's going to be calories.
It'll be gram degree. It'll be grams.
Oh, calories, degrees Celsius cancel. There we go. Got it? All right. So it's just going to be calories. All right. And now, as far as significant figures go, let's see what we got there.
Oh my god.
Yeah, I know. This
Don't
is
even
fun.
see that.
Watch.
That's what I don't like.
Yeah, again, if you got the significant figures wrong, you would be losing 0.5 point for the problem. But let's take a look at what the significant figures should be. This guy's got 4, right? That is an infinite number because he's a standard. And this guy's got 1, 2, 3, 4. So this guy should have 4 significant figures. How many does he have right now?
2.
He only has 2. So I have to show that he's got a 4 significant figure. I put a bar over that 0, right? That's a significant figure. Is that a big deal? No. Some of your professors in college won't care at all. Others will be sticklers about it. So it all depends. I'm just showing you the correct way. All right. Now, plus, let's do the same thing over here. 250 times 1 calorie. Again, grams will cancel. 250 times 1 is 250. 250 calories per degree Celsius TF. 250 times negative 10 is minus 2500, right? Degrees Celsius cancels this time and leaves me with just calories.
Okay, I have this. This is right so far.
Does that look good?
I have all this.
Yay.
I have the wrong answer.
We're not. That's why I said it's going to take 1, 2, maybe 3 steps before we're done. Okay, that's only the first step. All right. Significant figure-wise, he's got 3. He's got 3. He should have 3. So that bar again has to go over that guy. Remember, significant.
Isn't 350 only 2?
Huh? What?
Is it 250 only 2?
250 had the decimal point right here. See it?
Oh,
So that is 3 significant figures.
that's that.
You can't really see it, but it should be right there. All right. So there you have it. Now, that's your first step, distribution. We're distributing across these things that are in parentheses. Now, we're going to combine like terms. That will be the next step. Combining like terms, this guy's the same as that guy, right? So we'll combine him. 120 calories per degree Celsius TF plus 250 calories per degree Celsius TF is 370, you said?
I subtracted that.
Ah, there you go. There's your mistake. So you found it. 370 calories per degree Celsius TF. Negative 12,000 and a negative 2,500 is negative 14,500. Is that right?
Yeah.
And that's in just calories. And then the whole thing still equals 0. So that's the second step. All right, now the last step is to get your variables on one side, your numbers on the other, and basically just solve for the variable. So let's do that. I'll use blue this time. I should have used blue there. Anyway, whatever. So I've got 3. I want to keep my variable positive. Is he positive here?
Yeah.
So are you sure?
Yes.
Are you sure?
Positive.
You're positive. 370 calories per degree Celsius TF equals positive 14,500 degrees Celsius. Correct?
Calories.
What's that?
Isn't that calories?
This is no, it's not in calories. 14,500. I shouldn't say. If I wrote calories, that was a mistake.
You wrote calories up top.
Oh, wait. That is calories. That is calories. If I wrote that's right. That's calories. Sorry. This is calories. All right. Now, I said keeping my units was a benefit because if I have calories there, I know everything works out. Because what am I going to do now? Divide both sides by 370 calories per degree Celsius. 370 calories per degree Celsius. The calories will cancel over there, won't it? The degree Celsius was on the bottom of the bottom, so that makes them on the top. And that gives me TF equals what? 39 point what? 2. Calories canceled, degrees Celsius. There's your answer. So it was at least 3, looks like 4 steps here. 1, 2, 3, 4 steps to be able to get that final answer. And if you're not meticulous about this stuff, you are going to make dumb mistakes and get answers like 110 or negative 370. Okay.